Hi guys, welcome back. In this video, we're going to be tackling some optimization problems. So in my current calc class, we're getting into the optimization section for the first time. And these problems tend to be pretty difficult. When you're learning optimization for the first time, it is pretty difficult. I remember that when I took the class, it was the first time I remember actually struggling with calculus. And a lot of my classmates said the same thing. And a lot of my current students say that as well. So I thought it would be nice to go over some of the more complex optimization problems to help us understand how optimization works as a whole and how to use it to solve real world problems. And it's probably the most useful application of derivatives that we have. So it's definitely in your best interest to be really good at optimization. So just in a general sense, what is optimization? So to optimize something, just in a general sense, it means to get the best possible result. But in a calculus context, things get a bit more specific. When we're talking about optimization in a calculus context, it means we're trying to get either the smallest value possible for something or the absolute largest value possible. That's what optimization is in a nutshell. And we're going to be using our knowledge of derivatives to help us get that result. So like I said, it's a really useful tool to have in your arsenal. I recommend you practice this again and again until you feel really comfortable with the topic. So let's get right into it. So this problem tells us that we have, it says a farmer wants to fence an area of 1.5 million square feet in a rectangular field, and then divide it with a fence that's parallel to one of the sides of the rectangle. And we want to minimize the cost of the fence. So in every optimization problem in this class, you're going to have two quantities you want to keep in mind. We're going to have something that we want to optimize, and then we have what we call a constraint. So a constraint is going to be something that cannot change. It's going to be a fixed value that we cannot change at all. That would be the constraint. And then the other quantity is the thing that we're trying to optimize. So you want to just get really good at looking at clues in the problem to decide what's the constraint and what the thing you're trying to optimize would be. So it looks like this is going to be the constraint right here. We have an area of 1.5 million square feet. So this cannot change. The area is fixed, it has to stay this quantity, this many square feet. So that would be our constraint. Constraint is going to be area. And we have that written over here. Area is 1.5 million square feet. So we want to create an expression for this because we can't sorry, a bit tongue-tied today for whatever reason. I don't know why. This usually doesn't happen. We want to create an equation for this because without an equation, we can't properly use calculus to arrive at the answer we're trying to get. So area, of course, is just going to be base times height of whatever the region's supposed to be. So we have this part is going to be x. And then the height of the figure is y. So area is just going to be xy. And then we have another quantity that we have to consider too. We're trying to minimize the cost of the fence, which means we want to minimize the amount of material used to build this fence. So we need to consider not only the perimeter of the figure, but the length of this fence, this piece of fence that we're using to divide this in half. So we want to create an expression for the total amount of material needed to create not only the outer fence, but the piece of fence in between, in the middle of this area. So this is going to be perimeter is, well, it looks like we're going to have 3 of these y's to consider. And we're going to have 2 of these x's. We have 1 length of x on top, and we have 1 length of x on the bottom. So we have 2x plus 3y as our expression for perimeter, plus the area, plus the thing in the middle, the extra piece of fence in the middle. So 2x plus 3y. So now what we want to do, we want to take the quantity that we're trying to optimize. And before we even do that, I kind of just want to label things real quick, just to make it clear what can't change and what we have to change. So this area is our constraint. And then this perimeter is the quantity that we want to optimize. All right. So we have to take the derivative of the thing we're trying to optimize, because if we take the derivative, we'll be able to find either an absolute maximum or an absolute minimum, depending on what the problem is asking us for. And we'll get more in depth about what that really means and how to get there after we do these next few steps. So we need the derivative of this quantity that we're trying to optimize. We always take the derivative of the thing we're optimizing. In this case, it's p. So let's take the derivative of this expression. But before we do that, we have to put things in terms of just one variable. It doesn't work having a function in terms of two different variables. That's something we're not going to deal with in this class. So we need to figure out a way to put this perimeter in terms of only x or in terms of only y. So what I want to do is I want to take this constraint right here. I want to solve for y. And I can accomplish that by dividing both sides of the equation by x. So once we do that, we get y is equal to 1.5 million divided by x. And now that we have that, we can do a quick substitution. We can substitute this value in for y, in for this value for y, and then we're going to have a perimeter in terms of only x, and then we'll be able to take the derivative. So moving forward, we're going to get, whoa, sorry, wrong tool there. We're going to get p perimeter is equal to 2x plus 3 times y, so 3 times y, so 3 times this entire thing. Divided by x. So before we continue, let's multiply. So we're going to, when we multiply 3 by this part of the equation, we're going to get 4.5 million over x. And I'm going to be lazy. I'm not going to make a new line for this. I'm going to just modify the existing line. Strategic laziness is what I call that. So we have a perimeter in terms of only x, which is really, really nice. We can now take the derivative the way that we're used to doing and get a result. So let's go ahead and do that right now. We're going to take the derivative, and then we're going to find critical values of the perimeter, and that will help us get the result that we're looking for. So if we take the derivative of this, I'm just going to call this p prime. We're going to get derivative of 2x is 2. And then we're going to have to use the quotient rule for derivatives to get the derivative of the second term. And when we do that, we get negative 4,500 over x squared. And now that we have the derivative, we want to set the derivative equal to 0, and that will allow us to find the critical values. So set that equal to 0. And then I'm going to apply more strategic laziness. I'm going to just change this. I'm not going to make a new line. I'm going to modify this so that we're in a position to solve for x squared first and then solve for x. So I'm going to take this entire quantity. I'm going to add it to both sides of the equation. And when I do that, we get something that looks like this. Easy enough. And then from there, we want to multiply both sides of the equation by x squared, and then divide both sides of the equation by 2. So when we do that, we get x squared equals this quantity divided by 2. Here, I'll write it. So 4,500,000 divided by 2 is 2,250,000. Yikes, my other class is going to start really soon. I hope I can finish this before then. So now all we need to do is take the square root of both sides. Square root of the left, square root of the right. So the radical and the exponent on the x side cancel each other out, giving us just x. So this is our critical value, but we want to simplify it a bit to help us make a little bit more sense of what's going on in the problem. So let's simplify it. We're going to turn this into square root of 225 times 100 times 100. And we're going to give every factor its own radical. You get a radical. You get a radical. Everyone gets a radical. I'm sorry. I think I'm funny. I think I am, but apparently I'm not. So my apologies. So now let's simplify this. So square root of 225 is 15. So we're going to have 15 times 10 times 10. That's 15 times 100. We get 1,500 for x. So this right here is our critical value. But We are humans, we make mistakes, we don't do things perfectly all the time. We want to make sure that this truly does give us the minimum. So the best way to do that is, well, in some cases, you could take the second derivative. And if you get a positive constant for the second derivative, that would imply that the entire graph is concave up, which means you have a minimum. Otherwise, if you take the second derivative and you get a negative constant, that would mean that the entire graph is concave down, and then that would have to be an absolute maximum. But the problem is, when we take the second derivative, we're going to get something that's pretty complicated. We're not just going to get a number. We're not going to get a constant for the second derivative. So that is not really the best approach to do here, not the best strategy. So what we can do instead is something called the sign chart. And this is the main method that my teacher taught me when I first took AP Calc in high school. We never did the second derivative test. We always just defaulted to this sign chart. So this sign chart is a model of P prime. This is the derivative of the perimeter. And we know what happens when we plug in 1500. We know because 1500 is a critical value, that tells us that we have a derivative value of 0 when x is 1500. So we always start with that. We always start by labeling the critical point. It gives us a derivative of 0. Now the trick is to pick a value that's less than the critical value, pick a value that's less than 1500, and then pick a value that's greater than 1500 and analyze the derivative of both of those locations. So I'm going to apply more strategic laziness here, and I'm going to plug in 1 into the derivative. But I did something that you should never do. I manipulated the derivative equation, so I don't have that anymore. So my own personal laziness is coming back to bite me, and I'm feeling it right now. So what I have to do is I have to go back and write the actual derivative because I'm a horribly lazy person. So derivative is 2 minus 4500 over x squared. All right, so P prime of 0, we want to just plug in any value. So 0 works really nicely, but in this situation, we can't do that because it would result in the 0 in the denominator. So instead of 0, I'm going to pick the next easiest value to work with, which is 1. So I'm going to find the derivative at x equals 1. So I'm going to plug in 1 over here, plug 1 in for x over here. We're going to get 2 minus 4.5 million over 1. So we don't really care about the value. The only thing we really care about is whether it's positive or negative. So 2 minus 400, I can't talk, I apologize. When we plug in 1 for the derivative, we get 2 minus 4.5 million, which is absolutely negative. And I want to be proper with my notation. So P prime of 1 is negative. So once we have that information, we go to our sign chart, and then what I do is I just put a big minus sign right there to show that our function is decreasing on this interval. We're decreasing all the way up until we get to this critical value. So now what we want to do is we can typically just pick a value that's greater than 1500, plug that in, and verify that we get increasing behavior on the region. But the math gets kind of hairy. What I want to do instead is take the limit as x approaches infinity of our derivative, because we could pick this value, we could pick 1501. It would be a lot of tedious busy work. Same thing if we pick any of these values, but theoretically, what if we picked a number way out here? What if we picked infinity? Theoretically, if we picked infinity, what would we get? So we're going to take the limit as x approaches infinity of our derivative of P prime. So let's look at P prime real quick. Let's ask ourselves theoretically what would happen if x got larger and larger, if x theoretically tended to infinity. So any number over infinity converges to 0. So this would be 2 minus 0. That would be a positive value. And again, I want to be proper with the notation. So this would be positive. It's this limit as x approaches infinity that tells us that this would be positive. So because that is positive, it's going to be positive on this entire region. So I'm going to make a big plus sign to show that this entire region is positive. That's probably the sloppiest circle I've ever made. It looks like one of those beanbag chairs. Like at the mall in my town, there used to be a place called Love Shack. And this looks like a dude who just sunk so far into the beanbag chair and he's just blissfully enjoying the world. He's vibing. But enough of that. I'm wasting way too much time right now. I'm sorry. So we know that we have decreasing function behavior right before the critical value, and we have increasing function behavior right above the critical value. So let's just take a minute and think about what that means in the context of this problem that we're given. It means that our perimeter is going to be decreasing, and then it hits 0, and then perimeter is going to start increasing again, which verifies that we really do have an absolute minimum. So the whole reason we did that sign chart is to check our work. I said that this produces a minimum, so I decided to make the sign chart to prove that, and we were able to successfully prove that this is true. We were able to successfully prove that x equals 1500 really does produce the absolute minimum surface area, and therefore the absolute minimum cost of material. We'll keep in the area the same. The area doesn't change. The area is still 1.5 million, but the surface area we create, why do I keep saying surface area? The perimeter is a true minimum, and it's the sign chart that tells us that that's true. So now we just have to find one more bit of information. We have x, we want to find y. So we can take this area equation. We have 1.5 million is equal to xy, x times y, and we already know that x is equal to 1500. So now we're going to divide everything by 1500. So if we divide by 100, we get 15,000. If we divide it by 15 on both sides, we get 1,000. So we get 1,000 equals y. So the complete solution would be this. These dimensions produce the smallest cost of the fence. And I was thinking I would maybe make this video with 2 problems, but my next class is about to start in about 30 seconds. So I'm going to leave it at this, and then I'm going to upload a new video for another optimization problem. So stay tuned. See you in the next video.